So this week's Fix It Friday is kind of about the ideal gas equation, but it's also just about calculation questions in general, because there's a lot of errors in this question that are actually not related really to ideal gas calculations at all. So the first one, in fact, is the equation for the reaction between sodium and water. So it could be quite tempting to make an oxide. This is quite rare actually to do for group 1, because most people know that group 1, for example, sodium, would make a hydroxide. It is quite common though, if you think about it, when people do group 2 plus water and they know that it makes hydrogen gas, it can be quite common for students to write CaO instead of CaOH2. It's a lot easier to balance for a start. So this only happens if you react calcium with steam, so hot water. So the big thing to remember is that when you react a metal with cold water, you always get the hydroxide, not the oxide. Now, actually, it doesn't make a difference to the balancing of the equation in terms of the ratio between sodium and hydrogen. And also, it doesn't actually matter because this student has not taken into account the balanced equation, and we'll come up to that in a moment. But the next problem with the calculation is the conversion from milligrams to grams. That should be divided by 1,000, which means it would be 0.25 grams. That would then go into my mole calculation, and that would give me an answer of 0.0109 moles. But that is moles of sodium. So it's a really good idea when you're calculating moles and you're using balanced equations to just put the symbol or the formula for what it is that you've just calculated. Otherwise, you can forget the next step, which has been missed in this calculation, which is the ratio between sodium and hydrogen. So 0.0109 moles of sodium is going to make half as many moles of hydrogen, because we've got this relationship, 2 moles of sodium and 1 mole of H2. So we're going to divide it by 2, which gets us 5.45 times 10 to the minus 3 moles of H2. That is our gas, so that's what's going in the ideal gas equation. Okay, let's have a look at the rearranging. The rearranging has been done correctly to find volume. So PV equals nRT, and therefore V is equal to nRT divided by P. Putting in our numbers, now obviously the moles is wrong, but we would get an error carried forward mark for that. 8.31 is correct. Now let's have a look at the temperature. This is something else, and you really got to get in the habit of spotting it, because if you're someone who does this, you've got to try and just check, double check your numbers. This can happen when you're a little bit stressed in the exam. Up here, we've got the correct calculation of Kelvin, but down here, we've switched the numbers around and written 289 instead of 298. So another problem's come up in the calculation. Then we've got the pressure. So far we've converted units for Kelvin. We don't need to convert units for moles or the gas constant. But pressure, the units for pressure are quite important. And you may have spotted 101, which is still in kilopascals, and considered that to be a problem with the equation. Now actually, depending on the mark scheme and depending what the question asks for, it is not necessarily a problem so long as you are aware of how your units interrelate. So actually, if the number of moles was correct and the Kelvin were correct, then this student has written their answer in decimeter cubed. That would actually be the correct units of volume if we used pressure in kilopascals, and sometimes if you know what you're doing, that can be a useful shortcut in the ideal gas equation, particularly if we're just doing, say, a multiple choice question. Let's just look at how we can use units in that ideal gas equation, just to help us with a little bit of a shorthand in terms of like when we can shortcut and when we can't. If it asks you to substitute units in, be really careful and make sure that you're aware what they are. The important thing is to never just take the numbers in the question and shove them in without thinking about it. The normal units for pressure and volume are pascals and meters cubed. Now let's imagine for a second that the units given in the question are kilopascals. That's pretty common because that's actually a more sort of sensible sized unit to use when we're talking about atmospheric pressure and similar pressure. So to get from kilopascals to pascals, the conversion is I would times that by 1,000 before I put it in my ideal gas equation. But commonly, not all the time, but commonly, the units for decimeter cubed are what we use for measuring gas volumes, or certainly the volumes of containers, for example, that a gas is occupying. And to get from decimeter cubed to meters cubed, I'm going to divide by 1,000. So can you see that this means that PV in terms of pascals multiplied by meters cubed is equal to PV in terms of kilopascals multiplied by decimeter cubed. And that is because a decimeter cubed is 1,000th of a meter cubed, but a kilopascal is 1,000 times a pascal. So the times 1,000 step and the divide by 1,000 step actually cancel each other out. This is relatively useful simply because we're relatively happy, I think, most of the time, because we do it so often in other calculations. With dividing by 1,000 to get from centimeter cubed to decimeter cubed, it's perhaps a bigger calculation leap to divide by 1,000,000. In the question that we just did, though, the question was asking for centimeter cubed. So although the question would get some error carried forward marks for writing the volume in decimeter cubed, which was correct because they used kilopascals in the equation, it's not the actual final right answer because it needs to be in centimeters cubed. This is only a shortcut to use if you're confident in knowing what you're doing, and maybe in a shorter question rather than in a large 6-mark question.